Let's look at an example. Let's look at a typical projectile motion example where I'm going to throw particle or an object in the air with a particular initial velocity v naught, whose magnitude is known, and a particular angle theta. So obviously this is a nice parabola, and I would like to investigate a couple of key points. The first key point I'm interested in is the top of the parabola, which I will call A. And the second point is point B, which is the time at which right before the particle hits the floor. Okay, that doesn't look too symmetric, but just try imagine it's symmetrical parabola. To make my life simpler, I will choose a coordinate system which I will center such that at t is equal to 0, my initial position x naught is 0, and my position in the y direction is also 0. So I'm going to center it right there, just from convenience. And again, v naught is given and theta is given. So as soon as I know those two guys, first thing I know I can do is obtain the initial velocity in the x direction and the initial component of the velocity in the y direction, because I know those two are going to show up in my equation of motion. So v naught x will be v naught cosine theta, and v naught y will be v naught sine theta, which are known if theta and v naught are given to me. Okay, so what about point A? What's interesting about point A? Point A is the point or the time where the particle has reached the highest point in its trajectory, which means that at this particular point, that particle doesn't go up anymore, neither go down. It's like stuck in between those two states, quote unquote. So we know that at this particular time or position, the velocity of that particle is horizontal only. Because remember, we start with the initial v naught y, and then as the particle goes up, the acceleration, which is opposite in direction, will change and minimize the magnitude of the velocity until it reaches 0. And then it's going to keep going, and this time increase the magnitude of the velocity in a negative direction. And we know that at the top, the acceleration will actually change the direction of the Vy. So at point A, Vy is equal to 0. Hey, that's a nice condition. Let's use that. Let's remember which equation involved Vy so that we can use that boundary condition. Remember Vy by definition was equal to V naught sine theta minus gt. Let's see what comes out of it. If we replace and apply this formula at point A, then really this becomes the y component of the velocity at A. Those two are constant, minus t, and I will write ta to remind myself that this refers to the time that it took for position A to be reached. So really this will give me ta. Since at A my Vy is equal to 0, this is equal to 0. I know V naught, I know theta, I know g. Bang, let's get ta. Ta is therefore, as I solve for it, I'm going to get V naught sine theta divided by g. So it's nice, by using an important and interesting property of this particular point at the top of my trajectory, I was able to deduce how long is it going to take to go from this position, initially O, to A. And the time can easily be obtained by computing V naught sine theta divided by g. All three variables being given. V naught is given, theta is given, g is 9.8, no problem. And it's positive, so it looks good. Okay, so we know how long it's going to take to reach A. We know the velocity at A. What else are we interested in? Vx? What is Vx at A? Well, we already know this, the answer to this. We know that Vx doesn't change as a function of time, therefore Vx at A is the same as the initial component of the velocity, which is V naught cosine theta. No problem. So we know Vxa, we know Vya, we know the time it takes. What about its position? Ya. Well, let's use an equation that involves position. We know of one, y is equal to y naught plus sine theta times v naught t minus 1 half gt squared. Let's evaluate this equation at ta. So at point A, this equation becomes ya is equal to y initial. Y initial, remember the way that I set up my current system is to make my life easier, 0. This goes away. Plus v naught sine theta t, and this t refers to ta because I'm evaluating this equation at point A, minus 1 half gta squared. So that's nice. Since I know ta, I can replace my ta here, here, and this will give me the height of my particle. Let's do this. Ya will be v naught sine theta. My ta is v naught sine theta over g minus 1 half g ta. No, it's being squared, so we have to square the whole thing. V naught squared sine theta squared g squared. Okay, let's clean up a little bit. We have v naught, so that's v naught squared, sine squared, we still have the g. Here we can get rid of 1v, v naught squared, sine squared theta, 2g. Whoosh, whoosh. This is nice. So, same, we can combine the two, v naught squared, sine theta squared, 2g. Bang, done. Again, v naught is a constant, theta is a constant, g is a constant. We're able to figure out how high the ball is going to go. Very nice. We could go and try to figure out the x component. The x component will be, so we need to use the equation of motion of the x. X will be x naught plus v naught cosine theta t. Again, x naught was 0. We evaluate this at x at a, so at point a, x becomes xa. V naught doesn't change, cosine theta doesn't change, but this one is ta now, which we remember. Yes, yes, yes. Yes, v naught sine theta over g. So xa will be v naught cosine theta. Jesus. Yes. There you go. Bang. Okay. Let's rewrite this as v naught squared. And then I would like to use an identity, so I'm going to multiply this equation by 1. I can do that, right? I can multiply everything by 1 without changing it. But I will replace 1 as 2 over 2. So I'm multiplying this equation by 2 divided by 2, which is 1. I'm going to keep this one intact, but I'm going to merge this little 2 with this little sine and this little cosine, so I can replace 2 sine cosine by sine 2 theta. Just to make it pretty. But you don't have to, it's up to you. Okay, so now I got the position at A. So I know this. XA. Okay, let's look at this point. Point B. Well, what's interesting about point B? Well, point B is right there. And in this particular example, it's at the same level as my initial position. So in this particular coordinate system that I chose, the y component of B is obviously 0. Let's use that as a condition. Let's pick the equation that involves yb. This is going to be the equation of y as a function of time. Y is equal to y naught plus v naught sine theta t minus 1/2 gt squared. Let's evaluate this at point B. This will become yb. Y naught is 0. This will become tb, and this will become tb. And let's use the fact that yb is equal to 0. Therefore, this is equal to 0. Now this is quite nice because now we can solve for the time. And we're going to have 2 times. Let's factorize tb. We're going to have tb times v naught sine theta minus g over 2 tb is equal to 0. This will give me 2 solutions. tb is equal to 0, or tb is equal to v naught sine theta multiplied by 2 divided by g. How can we have 2 solutions? We have 2 solutions because this condition actually applies to 2 points. Point B and initial time. And initially, what was my time? T is equal to 0. That's the one. Therefore, we know that's not the one we want. This is the one that it will take to reach position B. Now, let's look at this carefully. Let's capture it, because by the time I move up, I'm gonna forget it. Let's compare this with the time it took to reach position A. That one. Look at those two guys. V naught, V naught, sine theta, G, G. The only difference is a factor of 2. That means it took twice as long to reach B. Aha, well, that's interesting. Let's go back to our graphs. It means that the time it took to go from this position to this position is half the time it took to go from this position to this position. This is true only if you have a nice symmetry, which means that the level at which you launch the projectile is the same as the level at which it lands. If the projectile will go down at a lower level, the symmetry is obviously broken, the result will be different. But if those two initial and starting point are on the same level, we have a nice parabola which is symmetrical. The time it took to go up will be the same as the time it took to go down. So TB will be twice TA. Okay, makes sense. What else? We know the time. Let's figure out velocity, Vy. So let's find an equation that involves Vy. Remember, Vy is V naught sine theta minus gt. So we can evaluate this at point B. This will become the y component of the velocity at point B is equal to V naught times sine theta minus gt, and this must be the time it took to reach B, which we just obtained. So that's nice. Let's just plug it in, and we'll have V naught sine theta minus g to V naught sine theta g. We can cancel the g's, and we can combine those two terms, and we end up with minus V naught sine theta. And that looks familiar. Whoops. Oh, where'd it go? Here we go. So what do we see? Again, due to the symmetry, which is only true in the case where you satisfy this, and the fact that the level is the same initial and final, the initial velocity at this particular time in the y direction will be exactly the same in magnitude as this point, except here is going up and here is going down. So the y will be going down while the y here is going up. But again, remember, the x component will never change, so the x component will still be v naught x. Again, if you're trying to shoot a higher position, or the end is going to be lower, the symmetry is broken and the result will be different. So in this particular case where we have a nice symmetry, let's clean up my mess. Uh, the final velocity of the object right before it hits the ground is exactly the same in magnitude as the initial velocity in the y direction, except with a minus sign that tells us that its direction is going down, opposite to my coordinate system. Again, the x component will never change. This will stay a cosine. Okay, now what about, well, the y we know it's 0. What about the x then? xb. Now that's interesting. I can use my equation of motion for x, which was x naught plus v naught cosine theta t. Yeah, that looks familiar. Okay, so evaluate at point B. This will become xb, which is my position at point B. X naught in my case is 0 because I center my coordinate system at t is equal to 0, x equal to 0. And this t must become the time it took to reach B, which is that one. Let's substitute it. Let's see what comes up. xb is going to be equal to v naught cosine theta 2v naught sine theta divided by g. Can we cancel stuff? Oh, yeah. No, but we can reuse and making it as pretty as before. Remember, 2 sine cosine will give me, and I'm going to combine the v naught and replace 2 sine cosine by sine 2 theta divided by g. Now, question for champions. Symmetry. We know it takes twice as much time to go from here to here than it takes to go from here to here. As you can guess, if it takes this distance, this one must be the same. Therefore, we expect xb, for this particular case, again, where this is leveled, to be equal to twice xa. Let's go check. Xa. Ooh, yeah. V naught squared. Yep. We're just missing a factor of 2. So it's all good. It's all good. Okay. Now let's keep things a little bit more general. I would like to ask myself concerning the range in general. That is, I would like to express the range, which is how far my particle is going to land, but I don't want it to be dependent on time. As you've noticed, all our equation of motion, let's recall them, that'll be a good memory practice. You got the x, you got the y, v naught sine theta t minus 1/2 gt squared, same as the v's. They're all function of time. So t acts like a parametric variable. What about I'd like to figure out the range, that is the position at which my particle will land, but I don't want to have to deal with time. Let's say I don't know nothing about time. So I like to express my position as a function of anything else but time. Let's say velocity or angle. Surely the angle matters, right? If I change the angle of my initial shooting, it's going to land at different position. So what would be interesting is relate the range or my x position with the angle. So let's see how we're gonna work that out. This is the one that will give me my range. So I will call and redefine x as r for range. And I don't want any g's in there. I want to get rid of t. Let's try to use this equation and this equation, combine them together, and get rid of t. So that y would be a function of x, maybe with a function of v, and especially function of theta. Now you could either replace t, solve for t in the y equation, plug it back into x, but that sounds like a lot of work, so let's use the opposite. Let's solve for t from this equation, the x equation, plugging it back into y. And let's use the case where, again, we start at x naught is equal to y naught is equal to t naught is equal to 0. So this equation, well, the one that was here, sorry, x is equal to x naught plus v naught cosine theta t. Let's solve for t. This is 0 in my case, so if I solve for t, t is equal to x divided by v naught cosine theta. Let's replace this in my y equation. Y is equal to y naught plus v naught sine theta t minus 1 half gt squared. Now again, I like to figure out the range. And when I know the range, the point that I'm going to consider is always going to be right here, at the end of the trajectory. In my particular case, since I start with those conditions, and I consider the case where it's level. So remember, whoa, hey, oh, sorry. So remember, I'm making several assumptions here. I'm making the assumption that I centered my current system at t is equal to 0, x equal to 0, x naught is equal to 0, and y naught is equal to 0. This allows me to simplify this term and this term. And I'm considering the case, more importantly, where my starting and ending point are leveled. Which, again, which means that this, at this point, which is the point of interest to calculate the range, my y is also equal to 0. And it is very nice, because now I have to solve for this. And since I don't have any constant, it's going to make my life easier. So I'm just going to replace my t in both places. And this will give me 0 equal to v naught sine theta and iso t. Hop, I'm going to put this x v naught cosine theta minus 1 half g t squared. So x squared v naught squared cosine squared theta. Ooh. Ah, let's clean up. Hop, hop. Those two guys cancel out. What else can I do? Oh, my phone is ringing. Sorry. But sine over cosine, that would be a nice little tangent. So let's have a tangent here. What about? Oh, that's it. So gx2 2 v naught squared cosine squared theta. Well, hey, I got an equation of position. Oh yeah, I forgot to calculate r. Well, same thing. As a function of theta. The rest is all constant. V naught is a constant, g is a constant. So really, I just obtain my position as a function of theta. So now I can check. Let's say if I no, let's not just check just yet, sorry. Now what I would like to do is I would like to figure out the maximum range. Let's solve for x. So let's have all the possibility of x. If I solve for x here, I got actually two solutions. If I factorize x, I get x times tangent theta minus gx 2 v naught squared cosine squared is equal to 0. Therefore, two solutions arise, x is equal to 0 and x is equal to tangent theta 2 v naught squared cosine squared divided by g. X equal to 0. Remember, I made the assumption that y was equal to 0, which also referred to my initial condition. So the first solution gives me my t is equal to 0 in case, which I don't care. This is the one that's interesting. Which I can simplify, guessing, yes. I can make it a little bit more prettier. Tangent is sine over cosine, so I can cancel one of the cosines. So I end up with sine theta on the top. And then again, I can combine the remaining cosine with the 2 and that sine. So this will give me v naught squared sine 2 theta divided by g. Yeah, that looks familiar. Okay, so this is a function of position, function of the angle. So what is this telling me? If my theta is equal to 0, that means I shoot horizontally. Well, that guy is not going to go too far. Actually, he's not going to go far at all, as theta is equal to 0, x equal to 0. Similarly, if I shoot straight up, the other extreme, theta is pi over 2, therefore 2 theta is pi, and sine of pi is 0. Let's look at cases in between. Now I know that as I increase my angle, I'm going to go further and further. We will see that eventually, as you pass a particular angle, you will start to see this. So there's going to be an angle which will give me the maximum range max, or x max. So as you increase the angle, the range is going to get bigger and bigger and bigger. Then you're going to reach the maximum value. And as you keep increasing the angle, the distance will get smaller and smaller and smaller again until you reach the other limit, pi over 2. So let's figure out that interesting angle that would give you the maximum range. How are we going to figure it out? Well, we can always use the results from calculus. Remember, if you have a function f and you like to know f max, what do? We take the first derivative, we set this guy equal to 0, we solve for the value of x for this to happen, and we take this special value and then we plug it back into f, and this will give us f max. So we're going to use the exact same standard as calculus to obtain maximum or minimum function of values. So in our case, x is a function of theta. So x is a function of theta, so I'm going to take the first derivative of this function with respect to theta. Yes, I'm not supposed to use that. Hop. And remember, x is a function of theta. Therefore, everything else will be treated as a constant. V naught is a constant, g is a constant. So this will give us what? Those two are constant. I can treat them separately. And now I need to take the first derivative of sine 2 theta, d theta. Well, that's easy. That's just going to give me 2 cosine 2 theta, because I've just used the chain rule. So now I am going to set this function equal to 0 and solve for that specific value of theta. So I'm going to set this equal to 0 and I'm going to solve for theta. This is a constant, 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 so I can multiply that whole equation by g divided by 2 v naught squared. All those guys are different from 0, therefore I can do that. Everything will go away and I'm left with cosine 2 theta is equal to 0. So for which value of theta is cosine 2 theta is equal to 0? Well, I can take the arc cosine, and the arc cosine of 0 is going to give me pi over 2. So I have 2 pi is equal to pi over 2. So if I solve for pi, I end up with pi over 4, which is, this is 90 degree, and this is 45 degree. Therefore, as I plug theta is equal to 45 degree in this equation, or pi over 4 if you're in radian, I would obtain the maximum range. So x max, or range, my maximum range, is v naught sine 2 times 45, which obviously will give me sine of 90, which is the maximum value of a sine, because this will give me 1, and therefore the maximum range is v naught squared divided by g. And yep. So again, we need to be careful. This result is only true if you're on the same level. Of course, if you're different level here or here, then this step would be different. And if this step would be different as you solve for x, you're going to have to use the quadratic equation. Therefore, those two solutions will be different. If those two solutions would be different, as you take the first derivative of this functional form of x with respect to theta, d theta, you will end up with different values of theta. So this results will not hold if your condition, whoa, come back, yeah, if those conditions are different. So remember that 45 angle giving you the maximum range is only valid for this particular case. But that was a nice application.